Um, this is going to be final sort of formal session where we're covering anything newish or finishing. We're going to finish off what we did last week. From now on in, we'll start to target a bit of revision, recap on the topics that we done earlier and so on in preparation for the exam. Okay, and you will have at least one, and that might only be one, but you will have a practice paper prior to going away for Christmas. Yep. So no, well, you'll have that prior to going away for Christmas. What I would hope would happen is when you come back, I think we got one session, and then that's the exam the following week, I believe, from memory. So what I would expect is for you to be able to say, look, I'm struggling with this question, this question, this question. We'll spend that session doing like a little tutorial around the things that you are least confident in with that exam paper. Yep. So that would be the way I would foresee it going. It's not available at the moment because I want to try and make it like the real paper. What's probably going to be now, there's 4 shorter questions worth 10 marks each up front. That will cover the whole, a wide breadth of what we've done. And then I would think a choice of 2 from 3 or 4 questions worth 30 marks each to go to a little bit more depth. Yeah? So you'll have some choice about the bits that you're better at to do in that second part of the paper. Okay? So that's my plan anyway. So what we're going to do today is just go through that last example we were looking at around the open and closed circuit tests on transformer, defining the parameters needed for the model. Okay? And then we're going to go over on the rig there, actually carry out open and closed circuit tests on that transformer. So 400 volt primary down to 230 volt secondary, I think. Yeah, 400 down to 230 is the nominal on that transformer. So we're going to find the model parameters for that rig transformer. Use a model we develop to analyse that transformer's performance under a particular load, and I've managed to find a load that is as close as we're going to get to fully loading that transformer, quite close to its maximum secondary current, and then we'll actually go back again and measure what output we get when that's fully loaded and do a bit of a comparison between the calculated results from the model and the actual results that we measure with instruments, and hopefully see, fingers crossed, everything crossed, that they concur with each other within the realms of practical considerations like the tolerance of the components and practical measurements and so on. Okay, so I think doing something like this brings that analysis to life and makes a reason perhaps for wanting to do it. That you know, we can analyse transformers and it does work. Okay, so briefly go through what we done on this subject last week. We can get these values for a simplified model that we discussed by doing an open circuit test, measuring the power input, the primary and secondary terminal voltages and the primary current, and then we do a short circuit test and measure the power input, primary terminal voltage and the primary current again. No secondary current that time. Okay, secondary terminal voltage that time, sorry. Just a note that care is needed when you perform the short circuit test to make sure that you don't overload the transformer. So you put in a much lower than normal voltage. When I've had a go at it yesterday, I think I input about 32 volts in that 400 volt transformer, keeping an eye on the secondary current to make sure it didn't go over the maximum 0.43 of an amp. So as long as you're careful, you're okay. So we're going to do that. Oh, I've got these. Right, let's take one. Got the slides. So do an open circuit test, measuring the wattage, the current, and the terminal voltage on the primary side, and the secondary voltage. And then we can do some calculations so we can find the apparent power. From that, knowing the measured power in watts, calculate the apparent power, get the reactive power. We can then use the secondary terminal voltage and the measured power to find the value for RC, the primary terminal voltage and the calculated Q to find a value for the XM, the magnetizing reactance. And we can use the two voltages there, EP and ES, to find out what the turns ratio A is. So that's what we get from the open circuit test, and we then get our model down here for the open circuit conditions and the losses that we have in the core, and for the magnetizing loss that we have even if there's no load connected to the transformer. Then we'll do a short circuit test, again measuring the power in, primary current, and the primary terminal voltage. We can use the terminal voltage and the current to find the impedance of the whole thing referred to the primary side. So that's going to take into account any leakage reactance on this side, but transferring it to the primary. Okay, and then we can use the power and the current squared to find a value for the copper losses on both sides. So it's the secondary referred to the primary and added to the primary copper resistance. So we've effectively, you remember last week we brought all the secondary stuff over to primary side, and then we added all the resistors together and all the inductors together. That's effectively what you're doing here. Those two component values combine both the copper losses from both the primary and the secondary of the transformer, and the leakage fluxes from both the primary and the secondary side of the transformer. Because usually we're not interested in what's happening with that. What we're interested in is what does it do to the output and the load. What's going to happen to the load, what kind of power output are we going to get, and what's the efficiency. So what actually happens within this black box that is all these values added together into one lump doesn't really interest us. Okay? You're all okay with that? Yeah? So then what we can do is take that model and connect our load to it. It's going to be Z dash, it's going to be the load transferred from the secondary to the primary. Better add that in formally, a Z dash that is. We can then analyse that circuit and transfer any values back using the transformer ratio to analyse this transformer. And we went on to start doing that in an example last week. We had this transformer where given some open circuit and short circuit results, and we started to use that, produce a simplified model of that transformer, and find some values when a 50 ohm resistor was connected. Okay, so moving on, the open circuit conditions, we had the measured power from the wattmeter, calculated S from the primary voltage, primary current. We got 10,350 VA. Use that value here to calculate Q, 9,062 var. Use the voltage value and the power to calculate the value for RC, 952 kiloohms, and use the voltage and the calculated Q here to calculate a value for the magnetizing reactance, 525 kiloohms. Lastly, we used the primary voltage and secondary voltage to calculate a value for A, the transformer ratio that we'll eventually need in our model. So did you all follow that calculation up to there? So then looked at the short circuit analysis. The data given is up the top here, 2,600 volts applied. The power measured under those conditions is 2,400 watts, and the primary current flowing under short circuit secondary conditions, 4 amps. Using that to find, using the voltage and current to find that a value for the impedance, 650 ohms, and from that calculated RP to be 150 ohms, and then calculated a value for XP, 630 ohms. So we've got our power triangle here that keeps cropping up, and that's where all that stuff comes from. What that enables us to do is put those values, 150 ohms and 630 ohms, into our model. This is a model where the impedance applied to the secondary has been transferred across to the primary side, so it becomes ZL dash, and a 50 ohm resistor we multiply by A squared, get 13,778 ohms, and that's what I've added on the circuit there. The next thing to do is to calculate the total impedance of that circuit. So we need to do some complex arithmetic here. We've got 2 resistor values and 1 reactance value. Do all that complex arithmetic, we end up with a total impedance of 13,942 ohms at an angle of 2.6 degrees. We can then use that impedance in simple Ohm's law, but with complex values, to find a current flowing in the primary side of this transformer, 4.95 amps at angle minus 2.6 degrees. This bit down here is where we've said that the apparent power being supplied by the generator is the current flowing in the primary times the primary terminal voltage. That voltage is 69,000 at angle 0. The current's got an angle of minus 2.6 degrees. So we get 341,550 VA. Remember what that is? That is a resultant S in a power triangle, which is made up of a Q and a P. So if we turn that into this is a horizontal component here, vertical component here. If we turn that into a rectangular Cartesian number with our calculator, the real part is how many watts, how much real active power we're getting out of the generator to this system. There's the real part, there's the imaginary part. Okay, so that's if you're going to do efficiency, you need to know what the power in is as well as the power out. Okay with that? So that's where we got up to, really. I've drawn the complete circuit, made a note over here that we're putting in that many watts, made a note over here of what ZL dash is. Okay, we're now going to do the arithmetic that will allow us to analyse the circuit, find out what the secondary voltage, terminal voltage and current is, and hence find what power we are dissipating in the load. From that we can find the efficiency of the transformer under these conditions. Okay, so we'll go through that now, and then you're going to mirror that analysis with the results from the real transformer over there. Okay, so where can we start? We calculated a current, didn't we? Can you just look back at the previous sheet and tell me what IP is?
IP is 4.95.
Yeah. So we know what the current is. How are we going to find out what the actual values are on the secondary side of the transformer? We've now got to transfer. What we want to know is not what E2 dash is, we want to know what E2 is, and we want to know what I2 is, which because we could say that flowing here is I2 dash, couldn't we? Which is the same as IP. Find I2. Yep. I2 dash is equal to if we've got what do we do to a current to transfer from secondary to primary? Are you sure? That is, yeah. It's I2 over A, therefore I2 must equal that. Yep. So I2 is equal to I, which is on back to our other results. I was 16 point something, was it?
Yeah, it's 16.6.
Okay. $16.6 times 4.95 angle minus 2.6 degrees. So Tom, I'm going to ask you, how do we do this arithmetic?
16.6 times 4.95.
Correct. Yeah. So we multiply these two numbers together, and that hasn't got an angle, but we add the angle, so the angle will remain angle minus 2.6 degrees. Those two numbers multiplied together equal and that's amps. Yep. Alright? Cool. So, our real secondary current, 82.2 amps. Okay? Yeah? And that sort of makes sense because this transformer, nominally 69 kV in, nominally 2600 volts out, means there's a step down transformer. So if you step down voltage, you step up current. So that's worthwhile remembering that little check, because if you got that, if you'd done what Tom suggested and divided by A, that wouldn't be true. Yeah? So that's a little, you know, if you remember the fact, if you got that knowledge in your head, if my transformers step down, we usually talk about it, what it does to voltage, step down or step up. But if it steps down voltage, it steps up current, because S on both sides must be balanced. Yep. So that's finding I2. Now we want the power, and to get the power we need the current and the voltage. We want to know the secondary terminal voltage. So we're looking at finding E2. Now, I would suggest there's two ways of going about doing this. So I'm going to split my page. Which way would you suggest doing it? Let's look at the circuit. We also now know the real I2. And we know what load we got connected on the secondary side. So how would you find out what the secondary terminal voltage is here? The real E2, not E2 dash.
Would you find E2 dash first?
Okay, tell me how to do that then, Luke. So you can go E2 dash is equal to I, and that's the, you can use the primary, you can call it the primary current, or you can call it I2 dash, don't make any difference, does it? Times ZL dash. So you can go down that route. That is 4.95 angle minus 2.6 times ZL dash is 13778, yeah? Okay, so do that multiplication, please. That's what E2 dash is, 68,201 volts at angle 2.6 degrees. How do we transfer the E2 voltage to make it E2 dash? If we were, when we went the other way, or if we were going from the secondary to primary, how do we do it? Is I times E2. So E2 must be E2 dash over A. Agreed?
Yep.
So do that arithmetic.
If you wouldn't know, how else would you just start I2?
That's the other method, Matt. Yeah? That's why I split the board. So you could do it this way or that way. It doesn't make any difference. So again, that's a useful check. Whichever way you choose, just quickly do it the other way with your calculator. Not necessarily writing it down, but do it as a check if you've got time to make sure you're right. So we're 68201 angle minus 2.6 degrees over 16.6. 4108 volts, angle minus 2.6 degrees. Does that make sense with the data you've been given? No. Oh yeah. E secondary, sorry. E secondary nominals 4106, so it does make sense. Yep. So round about that figure. As Matt said, he's spotted it, right part way through, you can also find E2 directly from I2 ZL. We calculated I2 to be 82.2 amps at angle minus 2.6 degrees. And we're going to multiply that by the connected 50 ohms. Equals 4110 volts, angle minus 2.6 degrees. How do they compare? 2 volts difference in 4,000. Don't care. Yeah? So, whichever method you choose, the other one's a quick check. Also, refer back to any data that you were given. Does it make sense? If you've been given nominal values, you're not going to hit the nominal value because we're talking about a real transformer here. We've got some losses. But are you close enough to say, yeah, that makes sense, and we're in the 4,160 mark, that is the nominal secondary voltage. Okay? Now, this is why I chose a resistive load here. I don't want to come under any complication of complex loads. If that's a resistive load, you'll notice that the angle of the voltage and the angle of the current, they're in phase with each other. They've both got an angle, but they could just as well be considered to be angle 0, because as a resistor they're in phase with each other. Yeah, because when we were on, even when we were on this side, when we dealt with this single resistor on its own here, we dealt with that only and found the voltage across it. That was as a per resistance, so it didn't change the angle of the current at all. So what we can do is, under those circumstances, S and P are going to be equal to each other because we've got no angle between the voltage and current. Do you all understand that? Yeah? And you'll see that in the practical, that there's no difference. We can measure also the VA, and the VA and the power within a point or two are exactly the same. Yeah? So, we could make a note there, because load is purely resistive, S2 is equal to power 2. So the S on the secondary side is equal to power on the secondary side. So therefore we can ignore the angles. S is equal to I2 times E2 that is current was 82 amps, wasn't it? 82.2 times 4108 equals 33767 watts. Hopefully that's less than what we were putting in. Yeah, I'm just gonna. Yeah, hang on, I'll just copy this first. Yeah. So our power output is 337 kilowatts. To 360 to three significant figures. Therefore, efficiency is equal to P out over P in. That's 337 over P in is 341 kilowatts to three significant figures. We multiply that by 100 to get it as a percentage. Just do that for us, please. So that transformer, as that data suggests, is 98.8% efficient. Yep.